Hello everyone, my name is Thiago. It's a pleasure to be here to present the status of the project In-Kernel solution based on XDP for 5G UPF, design, prototype and performance evaluation. First of all, who am I? I am a master candidate at University of Campina, Unicamp. I'm a military, my rank is captain. I am a software engineer. I had developed the software-defined radio in Brazilian Army, and I'm part of Aquinox team, developing a zero trust runtime Kubernetes security platform, and I'm an open source contributor at Cilium and Spidey community. So during this presentation, I'm going to follow this agenda. I will give an introduction, explain about Mac, 5G UPF, DPDK, and XDP. I will give a background about eBPF, XDP, and 5G UPF. I'm going to explain the design and implementation of the project, the performance evaluation, the results, and in the end, the conclusion and future work. So let's go to the introduction. First of all, I would like to define what is Mac. Mac is a multi-access edge computing. It's a network architecture that enables cloud computing and IT services at the edge of the cellular networks. We can think Mac like a local cloud that is deployed, for instance, in the base station. Another component that is important to define is the UPF. UPF means user plane function, is a 5G core component that is responsible to handle the user traffic. So the Mac and the UPF are totally related. So if you check here in the image, the UPF is responsible to receive the data from the base station and redirect it to the local cloud. So the Mac and UPF can be co-located. This is one example. And they may be sharing the same network and computational resources. So there are one challenge regarding for Mac 5G is to enable fast packet processing in the edge, because we have to concern about the commodity hardware that can be x86 ARMs. We have to concern about the hardware limitation, large difference in size, site, and scale from data center to a single device. And we have to concern about the efficiency resource utilization. So one of the main technology for fast packet processing is the kernel bypass. The kernel bypass moves the packet process from the hardware to user space. The well-known technology that implements this is the DPDK. But for scenarios like Math, it's not good, because the NICs must support it. As we saw, there are diverse infrastructure in Mac, and the pull mode drivers that keeps the CPU occupied even if there is no traffic. And we have to remember that the Mac, we have to concern about the efficiency resource utilization, and the integration with non-DPDK application. It's a hard task. So I decided to explore the express data path. The express data path moves the process into the kernel, and there are a lot of advantages using XDP. It's not a bypass, but in-kernel fast pass solution. No need to reinject the package. Does not require dedicated CPU to process the package. Can be compatible with all NICs, but with less performance, and can be dynamically reprogrammed without any service interruption. So, of course, there are some limitations. The program size is limited, but there are some ways to overcome. Unbounded loops, we have to define the size of the loops before the compilation. Send the same package on multiple ports is a problem, but there is a way to overcome this. And the package is a package-driven processing. So let's talk about some background about eBPF, XDP, and 5G UPF. I will explain what is eBPF, how XDP is related to eBPF. And I will give some 5G UPF architecture in order to understand the design and the implementation of the project. So here, what is eBPF? eBPF is a general purpose engine that is located inside the Linux kernel. It's a built-in. It executes bytecode safe. This bytecode is attached in some hook points after the compilation. It's attached in some hook points. And there are a lot of use cases for eBPF, for instance, observability, security, and package processing. For this scenario, I'm focused on the package process. So as you can see here, we have the process, the loader, that will load the bytecode of the eBPF. This bytecode is generated using CLang. We program the eBPF. We programmed the eBPF using C restrict language. So after we compile it, the bytecode, the process will load into the kernel. But after that, it will pass through the verify. The verify will check if there is any unbounded loop or if the program is access the memory correctly. After approved, it will just in time compile and it will attach in this hook point. So it's important to say that there is a key value structure that is responsible to communicate the user space and the kernel space in the eBPF program. So this structure is used for both. So what is XDP? XDP is a hook point, but it's located in the driver of your NIC. It's a special hook point that's located in the driver of your NIC. So it's important to say that this program is run before the socket buffer allocation. The socket buffer is a structure that stores the metadata of the package. So before allocate the socket buffer, the program is executed, and we can have a lot of actions. You can apply a lot of action in this program. For instance, redirect to another package, drop, or pass to the network stack. So that's why the XDP is so fast, because it's the lower level execution. Okay, let's talk about the 5G UPF architecture. Here is the 5G system architecture. As we can see, we have the UPF, and the UPF is connected through the control plane using the N4 interface. The N4 interface has this protocol, PFCP protocol. So basically, the control plane creates PFCP session in the UPF. And when the package arrives, 3 main blocks is executed. So first of all, it will look if there is any PFCP session related to that block, to that package. If there is any PFCP session, it will pass to another block that will find the PDR. PDR means packet detection rules. This packet detection rules has some information about if it will match with the header of the package. For instance, the source IP or the traffic endpoint ID, if this package is a GTP package, and so on. If there is a match, it will pass through by another block. So here it will apply some rules. The mandatory rules is the following action rules. So in the status of the project today, we are only handle the forwarding action rule. So the forward action rule is responsible to forward the package to the destination interface. So basically here is the package process flow in the UPF. Let's jump to the design and implementation of the project. The project was developed to develop using the XDP, okay, to implement the 5G UPF. And the key pillars is an open source library, in-kernel fast package processing using eBPF XDP, flexible, extensible, and programmable data plane, portable to different systems. It's a feature, a BPF feature that means compile once, run everywhere. It's very interesting, this feature that fits very well in the Mac scenario we have when we have diverse infrastructure spread on the edge. So here is some the minimum requirement that we define for the first version. Here we have the PFCP session, as I mentioned before, is composed by two rules, basically, the package detection rule and the forward action rule. This rule has some parameters, but the main parameters is this for the PDRs. This is the parameters that will match with the package, the source interface, the tunnel endpoint ID, and the user equipment IP address. So it will be checked in this block, as I mentioned before. And there is if there is a match here, it will apply the rules. That is the forward action rules. So the forward action rules has the logic to where the package will be forward. So here, as you can see, there is a forward parameters. We can create another header, or there is information about the destination interface. So it was based on the 3GPP release 16. And here, as we can see, we have the design of the high-level design of the implementation. Here we have the management layer and data path layer. The management layer responsible to receive the PFCP session request, creation request, and load the programs into the kernel. So every session, there will be a program inside the kernel that represents that context. And for this, we define some requirements, that session management, that will manage the PDRs and the FARs. So this layer is responsible for that. And traffic classification based on the PDR, and traffic forward based on the FAR here. So here is the data path layer, but with more details. As we can see, we have some eBPF maps here. Here we have one program. Here we have other program. This is the entry point. So it's mandatory in our solution. After that, we have for each PFCP session created, we have we will have a new program, a BPF program. So when the package arrives, it will parse the package, will find the eBPF program that is related to that session. It will look up the PDRs and will apply some rules. In this case, the forward action rule, and it will redirect the package according to what is defined here. As well as we have the MAC address for the next hope, and the redirect interface that will be forward. So here is some technology that was used during the project. If anyone wants to know more about the project, here is the link. So I'm going to show an overview about the structure of the code. Here we have the bin folder have the BPF tool. This tool is used to generate the skeleton that is used in the user space based on the eBPF program. So we have the eBPF program, and we use this tool to generate the skeletons. We have some CMakes here, some Docker files. This Docker file is used to generate the development environment. It's important. Some external library that we use. We are based in the libbpf. And some libraries for log, and this is for test. We'll explain later. This package is a folder that is generated using the CMake. Here we have the folder lib that will have the library and some binaries regarding to the test if you want to test. The source code, there is a BPF folder. The BPF folder, there are all code related to the BPF is there. So as you can see, we have basically two programs. The UPF XDP BPF, it's an entry point, as I mentioned before, and the session BPF. This session BPF is where the PFCP session is stored. We have here the user space classes. So here we have some classes in order to program the life cycle of the programs, and some abstraction regarding the session programs at the entry point. The skeleton that is generated using BPF2, some library for logging, and some wrappers for the BPF maps. And here we have some session manager class, session program manager, and so on. This class is responsible to manage the program, the session program, and this class is responsible to handle the PFCP session, the PDRs, the FARs, and so on. So there are also a test folder that has a API. This API was developed for testing. It wraps the UPF BPF library. We use this API for the test. I will explain later. And we have some scripts in order to deploy to make easier the life of the developer. In order to deploy the tracks and deploy the diff pairs and all things related to the test, I try to make the life of the developer easier. And here there is some code related to the tracks. We try to program all the tests. The test is not automated yet, but it's semi-automated. We have to execute some paths manually. And there are also, we are using the Google Test Framework. Here is the execution for the manage the PDRs, manage the FARs, and so on, and manage the session. Here is a execution that we used, the API that we developed to execute the test. Basically, there is two API. Is configure to configure the interface and create session to create the PFCP session in the data path. So let's jump to the performance evaluation. Here is the test that I was talking about. Basically, we have two machines. These machines has the HTTP API UPF BPF library, And there is a T-Rex traffic generator that is responsible to generate the traffic. So here is the configuration of the machines. Here is the steps. First, we run the T-Rex traffic generator. Run the HTTP API UPF BPF. Configure the interface using this API here. We configure this interface. After that, we create the PFCP session with this API. So after that, after this step, it will deploy the BPF program into the kernel. So finally, we will generate the traffic. And of course, there will be a PFCP session created because of this step. And we will handle the traffic and we will forward it to the destination interface to the T-Rex traffic generator to complete the loop. So in the end, we collect the metrics from this machine and this machine. Here is the create session API. This is the message that we send to the HTTP server. As we can see, we have information about the packet detection rule. Here is the packet detection information that I mentioned before regarding the source interface and user equipment IP address and tunnel endpoint ID. And here is the continuation of the message. As you can see here, we have the far and the forwarding parameters here for each far and the ARP table. So here is how the flow is generated. We use the one engine that has in the T-Rex. So here, if you want to know more about, I believe it's good to scan this code. But basically, we have a engine inside the T-Rex that we can programmable how the traffic will be created. So here is the program of this machine. The results, as we can see here, we have the scalability regarding the numbers of cores for downlink and uplink. And for 6 cores, we are using 61% of CPU, and here using 6% of CPU. So in this point, we had this. So as you can see, there will be almost 40% CPU available for other tasks. Here is one screen regarding to execution that it was created using Tmux. The left side is the T-Rex, the UI of the T-Rex. We have here some parameters, transmission, receiving. Here the port that is transmitting, and here the port that is receiving. We can compare the number of packets that was sent and the number of bytes that was received. Here is the number. Here, all this span is logged into the HTTP API UPF BPF machine, and we have the number of queues that was used in the test. The CPU load here is the HTTP server being executed. And here is the results of this execution. So, as I mentioned, as I presented here, it was developed a UPF based on XDP. It was a library to make easier the integration in the extension. It's an in-kernel processing. It's an open source implementation, so everyone can benefit of this implementation. It's based on 3GPP release 16, and we have a portability with core. It's not implemented yet, but we intend to implement as in the next few months. And also we have shown that with 10 megapixels per second was achieved with 6 cores using only 60% of CPU. So future work. We are working on the redesign, support multiple PDRs. We are trying to decouple the rules. As I mentioned before, there is one program regarding to PFCP session. So the PDRs and the FARs is all in this program, the BPF program. So the idea is to decouple this program, and doing this, we will have a flexible pipeline. So if you have a PFCP session and you want to add another rule, we don't need to unload all the program, all the PFCP session and load again. We just need to insert that new rule that represents that. We just need to add the new program, the BPF program that represents that rule. So we will do that without any service interruption. We are working on the compiling once, run everywhere. And we are working on the integrate with an open air interface that it's a 5G implementation open source. The next steps is to support QoS enforcement rule and test varying the number of packet size and the kind of flows. So here is one discussion that is open in the project. As we can see here, we have the UPF eBPF library inside the SPGWU of the OAI component. So if you are interested in work on that, please comment on this discussion, and we can have a good discussion in order to achieve this task. Some open questions. Is there any limitation to implement new functionalities, new features using eBPF like slicing? Scalability, how many sessions can be actively maintained by eBPF? How many flows can be supported? Testing, what kind of flows should be used? And that's it. Here is some reference. And thank you. If you have any question, please comment below or send me a message. That's it. Bye.